Hello everyone and welcome to my first YouTube video about maths. Today I'll be discussing the basic trigonometric functions and the three Pythagorean identities, which are discussed in AS and A2. But before I start, I must tell you that none of this is required by the A-level syllabus. These derivations are only for understanding, and the only reason I'm making this video is so that I can help more students understand where these identities and functions come from. So I have the functions you learn in AS marked in red, and I have the functions you learn in A2 marked in blue. So the functions you have in AS are sine theta, cosine theta, and tan theta, and the functions you have in A2 are secant theta, cosecant theta, and cotangent theta. And the Pythagorean identities that you have in AS, you only have one identity, and that's the Pythagorean identity. That's sine squared theta plus cosine squared theta is equal to 1. And in A2, you have a lot more identities, but for the Pythagorean identities, you have tan squared theta plus 1 is equal to secant squared theta, and cotangent squared theta plus 1 is equal to cosecant squared theta. Okay, so for starters, I've made a circle with a radius of 1 about the origin, with the center as the origin, on a graph. So this is the negative x-axis, this is the positive x-axis, this is the negative y-axis, and this is the plus y-axis. And you can see I've written the negative intercepts, and obviously the positive intercepts will be the same. So if I were to draw from the origin a line to any point on the circumference, I can safely say that since this is the radius and the radius of the circle is 1, this line is equal to 1 in terms of length. And I can define this angle as theta. So from this point, if I were to draw a vertical line to the x-axis, I would start to get something that looks a lot like a right angled triangle. So I'll just connect the origin with this line, and I have a right angled triangle. This right angled triangle can be used to find sine and cosine. So if this right angled triangle has a hypotenuse of 1, and since we know that sine theta is equal to opposite over hypotenuse, which in this case is 1, we get that the opposite is equal to sine. So I can write here that sine theta is the opposite of this triangle. And the same goes for the adjacent. So we know that cosine theta is equal to adjacent over hypotenuse. And since we know the hypotenuse is 1, we can just write 1, which means that for a triangle with the angle of theta and a hypotenuse of 1, the height is sine theta and the base is cosine theta. Now from here, I can draw a line from this point to the x-axis to make another triangle. I can connect these points, and now I have a triangle. And before I say anything else, I want you to know that this point that the hypotenuse is touching the circumference at is, since it's cosine of theta across and sine of theta up, it has the coordinates of cosine of theta, comma the sine of theta, which is pretty neat. So from here, I can continue, and I observe that the triangle that I also made mirrored has an angle of 90 degrees. And since we know that at any point on a circle, if I draw a tangent that contacts the radius, then the angle there will also be 90 degrees. And since we know that this triangle had theta and 90 degrees here, that means that this angle is 90 minus theta, and since this is 90 degrees, then this angle will be theta. And if this is theta, then this will be 90 minus theta. So now I have two triangles, which, as you can observe, you might have noticed that sine theta is the adjacent of this triangle, and it's the opposite of this triangle. So we can draw this separately for a better understanding. Okay, so I have two triangles drawn here. I can draw theta over here, and I can draw the right angle here, and I'll do the same on the other side to make it easier to understand. And notice here we had theta here, but here theta isn't on this side, it's on this side. So I'll draw the first triangle which we started off with, which had the hypotenuse of 1, which had adjacent as cosine of theta, and the opposite as sine of theta. And this triangle, which has the theta here, which means that the adjacent on this triangle is theta, sine theta. So this is sine theta. And in this case, I don't know the hypotenuse, nor do I know the opposite. But for our purposes, we only need to know the hypotenuse, which I will assume to be h. So we know that since these triangles, notice that this has the angle of theta, this has the angle of theta, this has a 90-degree angle, this has a 90-degree angle, and since both of these are same, the third angle will be the same in both of them as well. So these two triangles are similar by the property of AAA, which is angle, angle, angle. So I can safely say, by using the ratios of similar triangles, I can say that h over 1, which is the hypotenuses of the both of the triangles, and sine theta over cosine theta, which is the ratio of the adjacents of both of the triangles, I can get, since it's divided by 1, I can just ignore this, which means that h is equal to sine theta over cosine theta, which we know that is tan theta. So that means that this line on this triangle, which I found out here, which is h, is tan theta. So now on this triangle, I have derived both sine theta, cosine theta, and on a separate triangle, tan theta. So I have all of these. And now let's try to derive the other three trigonometric functions. So firstly, I'll draw another line here. And notice that this triangle that will be made here, this is 90 degrees. And since this angle is 90 degrees as a whole, this is theta, so this will be 90 minus theta. And since this was 90 degrees, if this is 90 minus theta, then this will be theta. So what basically happens here is that I get another triangle which is basically just flipped. So this will become sine of theta. So I just have this triangle but flipped here. And I'll do the same thing here that I did here, which is I'll draw a line from this point to the y-axis. So I can observe that if this is theta, since this triangle has 90 degrees here, this will be 90 minus theta and this will be theta. I can see that this also makes a right angled triangle with the opposite as cosine of theta, and I can use this again to derive another trigonometric function. Okay, so that triangle will use the base triangle we used in the start, which had theta over here. We'll write 1 as the hypotenuse, we'll write cosine of theta as the adjacent, and we'll write the sine of theta as the opposite. And then we'll take a look at that triangle we made, and we see that theta was over here, so that means cosine is the opposite. So we can write a triangle with cosine as the opposite to theta over here. And notice how in the other triangle we had similarity. We also have the same thing going for us here. If this is cosine of theta, notice that both of these are similar, how both of these were similar, by the same identity, which was AAA, angle, angle, angle. So if these triangles are similar, and we notice over here we want to find the hypotenuse again, we can label this h, and we can use the same ratio we used the last time. We can get h over 1 is equal to cosine of theta over the sine of theta. Now notice that in the other triangle we got h is equal to sine theta over cosine theta, which is tan theta. But this time we have a reciprocal of that, which is cosine of theta over sine of theta, which means I can write this as 1 over tan theta. Now, in math, we said that instead of calling it 1 over tan theta, we can simplify it and just call it cotangent of theta. So that basically means that cotangent of theta is equal to 1 over tan theta, which means that the hypotenuse of the triangle we just made is cotangent of theta. So let's go back to the circle we were on. We can see here that this was the hypotenuse. So I can safely write here that this is the cotangent of theta. Now we're going to derive the last two identities, and those are secant and cosecant. So let's start off by looking at this big triangle, the one that we have comprised of both of the right angle triangles. I have this drawn on somewhere else so I can represent it a bit better. But before we move there, I want to show that this is theta, this is 90 minus theta, and this whole thing is 90 degrees. So this huge triangle is also 90 degrees. Basically a right angle triangle. And that this is tan theta, and the height was sine theta, and this is 1. So we can move to the other side. And I have this triangle drawn here. We know that this was 90 degrees, that this was theta, and this is 90 minus theta. And we know that this was 1 and this was tan theta. So I basically have another triangle that I got from the two triangles, and for simplicity's sake, I'll take this triangle and I'll rotate it so that it's better for me to understand. So I'll adjust this in terms of the base theta orientation we had. And notice that on this, theta is here. So this is 1 is the adjacent. This is the adjacent. And this is the opposite, because this is opposite to theta. So this is tan theta. And notice that this again has the same angles as the starting triangle we started off with, which was theta here, right angle here, hypotenuse as 1, cosine theta as the adjacent, and sine theta as the opposite. So again, we have similarity between both of these triangles by the rule angle, angle, angle. So I can again use the rules of similarity to find the hypotenuse of this triangle to find one of the trigonometric functions. So what I'm going to do is I'll take hypotenuse over 1, which is the ratio of both of the hypotenuses, is equal to 1 over cosine. So now I know that the hypotenuse of this triangle is 1 over cosine. Now we have another name for 1 over cosine, which is secant of theta. So what the hypotenuse of this triangle basically is secant of theta or sec theta. So let's go back to the circle we were on. And on the circle, we took this whole triangle and we found this, since we already had 1 and tan of theta. I'll write these in red. So what I basically just found was this whole length over here. I'm having some trouble drawing this line. My apologies. This whole length over here, which was secant of theta. So basically this whole length is sec theta. Okay, so now we're going to derive the last trigonometric function, which is cosecant theta. And we're going to use this big triangle over here that's attached to the y-axis. So we know that the line touching theta is cot theta, and we know that the line with 90 minus theta is 1. So we can rearrange this triangle, and we know that this is 90 degrees. This thing over here is 90 degrees. So we can rearrange this triangle to better understand what's going on. Okay, so here we can rearrange this triangle. We know that this is theta. We know this is 90 minus theta. And this is a right angle. And we know that on theta, we have cotangent of theta. And on 90 minus theta, we have 1. So again, for better understanding, I'll rotate this triangle so that we can understand it a bit better. So I'll draw it in terms of the right angle being on the bottom right. And notice here that theta is the adjacent cotangent, I mean cot theta is the adjacent to theta. So I can write cot theta over here. And this one is the opposite. So now I have a triangle with the base as cot theta and the opposite as 1. So I'll assume the hypotenuse is h. And for the last time, I'll use the triangle we made in the beginning, which had the base as cosine of theta, the opposite as sine of theta, and the hypotenuse as 1. And again, I'll notice that these are similar by the identity triple A, angle, angle, angle. So I'll find the hypotenuse of this triangle. So we get hypotenuse over 1 is equal to 1 over sine of theta. I'll use the opposites for this one. 1 over sine of theta. Now, we can ignore the 1, so we know that the hypotenuse is equal to 1 over sine of theta. And another name we have for this is the cosecant of theta. So now we have derived all 6 of the trigonometric functions, trigonometric functions. Going back to the triangle on the circle, we can redraw this, annotate, You can see that this was the big triangle and this is what we were finding. So that means that this whole length is equal to, this whole length is equal to cosecant of theta. So now we have all 6 of the trigonometric functions derived from the unit circle, and now we will find the Pythagorean identities. Okay, so what I've done is gone ahead and drawn all of these right angle triangles that we got from the unit circle, and we'll be using all 3 of these triangles to derive the 3 Pythagorean identities. This was the first triangle we made, this was the first big triangle we made, and this was the second big triangle we made, which have all been labeled beforehand. So we know by the Pythagorean identity, which is that adjacent squared plus opposite squared is equal to the hypotenuse squared. So we'll be using this identity to find all of the Pythagorean identities. So for the adjacent in this triangle, we have cosine squared of theta, and the opposite is sine squared of theta is equal to 1 squared, which basically just means 1. I'll be assuming that 1 squared is 1. I won't write that because it's a bit redundant. So this is how you get the first identity, and all of the other identities are also derived in the same manner. So again, I'll just do the same thing. This is the adjacent, this is the opposite, and this is the hypotenuse. So 1 squared, which is just 1, plus tan squared theta is equal to sec squared theta. So this is the second identity, which we got from this triangle. And then from this triangle, we'll get our last Pythagorean identity, which is that cotangent squared of theta is plus 1, 1 squared, which is 1, is equal to cosecant squared of theta. So now I have the three Pythagorean identities that I derived from the unit circle, which I also derived all the 6 trigonometric functions from. So I hope this video was helpful for anyone who had trouble understanding where all of these identities came from and how we get these identities. For AS students, you have everything up till here except cotangent, cosecant, and secant. And for the A2 students, I will be making more videos, which includes the derivations for the compound angle formulas and the double angled identities. So I hope the video was good. If you have any critique for me, please leave it in the comments, and thank you for watching.